Ladies and gentlemen, distinguished guests, it is my honor and great pleasure to welcome to Comenius University in Bratislava the participants and guests of the Quantum Spacetime 19 conference. It is to any university's credit to organize important scientific events, especially if leading scientists from all over the world agree to participate. For this reason, I'd like to begin my short speech by warmly thanking the organizers for their hard work and preparation, and by thanking all of the guests for their active participants in the conference. It is also a pleasure for me to welcome everyone who has come to this public lecture. Today I have the special honor of welcoming among us an important scientist, mathematician, physicist, and philosopher whose ideas, reputation, and impact epitomize a unique and unquestionable brand of virtue and excellence, Sir Roger Penrose. Sir Penrose is undoubtedly one of the thinkers who have influenced our understanding of mathematical physics, the general theory of relativity, and the cosmology of the universe more than we are likely capable of appreciating today. His theoretical physical ideas are based on a singular expertise of mathematics, which has influenced many of his students, as well as theoretical physicists, such as Stephen Hawking, and mathematicians around the world, including the recently deceased Michael Etiyah. Remarkably, the inquisitive and probing spirit of our guest hasn't been limited to investigating the physical macro world and its entities, but has also focused on the micro world, and especially an attempt to reconcile physics with an explanation of the consciousness. An extraordinary trait of Sir Roger Penrose's scientific research is that, with the help of his imagination, he often finds solutions where others believe none exist, or that they are logically and mathematically impossible. Examples include not only the Penrose triangle, which he popularized and which inspired Maurice Escher, but especially the whole of his research in the field of non-periodic tiling. To conclude, from the position of the rector of the oldest and most important university in Slovakia, I would like to express my delight and support for the exceptional theoretical and experimental research ongoing at our university, the much rewarding international scientific cooperation, and the development of specialized theoretical physical as well as inter- and multidisciplinary research spanning all fields. I believe that this event will lead to further study, future cooperation, and will serve to inspire all areas of research. Therefore, Sir Penrose, allow me please once again to thank you for accepting our invitation to come to Bratislava and for giving us the opportunity to share in your ideas, time, and knowledge. I wish the audience an inspiring and enriching experience throughout. As a token of our recognition, gratefulness, and respect, I would like to present you with this commemorative medal of Comenius University, granted upon the 100th anniversary of the university's foundation. It is truly symbolic that you become the very first recipient of this award, as not only in the world #1, but also in the physical reality which grows out of it. Sir Roger Penrose, our space, time, and attention are yours.
Thank you, Mr. Rector, and now I would like to ask Professor Sabo, who is chairman of Quantum Space Project COAST, to open scientific program of this public lecture, please.
Thank you. Okay, good evening, everybody. It's truly my honor to have been asked to make this introduction to Sir Roger Penrose. Sir Roger is the Emeritus Rouse Ball Professor of Mathematics at the University of Oxford and an Emeritus Fellow of Wadham College in Oxford. He's a mathematician, a physicist, a philosopher of science, and as a mathematical physicist, he has made unraveling contributions to general relativity and cosmology. He was born in England and received his PhD from Cambridge in 1958, a PhD in mathematics under the supervision of the well-known algebraist and geometer John Todd. Shortly after, his interests from pure mathematics switched over to astrophysics, and since then, he has played a major role of our understanding of various phenomena in general relativity. He has truly revolutionized the mathematical tools that we use to study the properties of spacetime. So one major indicator of esteem as a mathematician or a physicist or as any scientist is when things are named after you. When you have so people might like to name things after themselves, that usually doesn't work, but when your colleagues name a development after you, that's a big measure of esteem. It's a measure of respect and acknowledgement. I have a list here of things that are either directly associated by name to Sir Roger or that are named after him. There are too many of them to go through, but I'll just go through a few of them that you might have heard of. There's the Moore-Penrose pseudo-inverse that came out when he was a student. There's the famous Penrose-Hawking singularity theorems, cosmic censorship, the Veil curvature hypothesis, the Neumann-Penrose formalism, of course, the famous twistor theory that he invented, the Penrose inequalities, the Penrose interpretation of quantum mechanics, the Schrödinger-Newton equations, the notion of spin networks, which is still used today in modern approaches to loop quantum gravity. He popularized the use of these things in general relativity called causal diagrams, and today they're known as Penrose diagrams. And the list goes on. There's the Andromeda paradox, conformal cyclic cosmology, and so on. And he's written popular books, semi-popular, as I've learned he likes to call some of them. And there's a book he wrote called The Road to Reality, A Complete Guide to the Laws of the Universe, which is a big, thick book summarizing his perspective on the laws of nature. Sir Roger has also been a philosopher of science. He's been interested in the connections between fundamental physics and human or animal consciousness. Again, there's several popular books that he's published on this. The famous one, The Emperor's New Mind, Shadows of the Mind, The Large, the Small, and the Human Mind. Another measure of esteem of a scientist are awards and honors. And again, here there's a very long list of awards and accolades that go to Sir Roger. So I've picked out a few. I hope I'm not missing any of his real favorite ones because I didn't want to list them all. But he won the Adams Prize in 1966, the Heinemann Prize in 1971. In 1972, he was elected as a Fellow of the Royal Society. 1985, he received the Royal Society Royal Medal. In 1988, he was awarded the prestigious Wolf Foundation Prize jointly with Stephen Hawking for their work on the Penrose-Hawking singularity theorems. 1989, he was awarded the Dirac Medal and Prize. In 1990, he was awarded the Albert Einstein Medal. 1991, the Naylor Prize of the London Mathematical Society. He served as president of the International Society on General Relativity and Gravitation from 1992 to 95. In 1994, he was knighted for his services to science. In 2000, he was appointed to the Order of Merit. 2004, he won the De Morgan Medal for the London Mathematical Society, and in 2012, he was awarded the Richard R. Ernst Medal from ETH Zurich for his contributions to science and for strengthening the connection between science and society. Another thing that Sir Roger is famous for is he's a very gifted speaker on all levels, both at giving a talk at a conference such as the one we heard earlier this week for scientists, and also for his public lectures. I first heard Sir Roger speak back in 1997. I was on my first postdoctoral position in Oxford. And it wasn't a public lecture, it was a colloquium. So, and the rooms were full. I actually didn't get to see him talk because it was so popular they had to use 2 rooms, and the second room just had a projector showing him. So I was in the room where you didn't see the real person. At that time, I was in the theoretical physics department at Oxford. Sir Roger was in the Mathematical Institute. So we didn't have much encounter with each other. But I still feel somewhat close to Sir Roger because 3 years later, in 2000, I moved to my permanent position at Heriot-Watt University in Edinburgh and became a colleague of Roger's brother, Oliver Penrose, who had been there long before me. So for the past 18 years, I've been a colleague of Oliver Penrose, who's also a mathematical physicist, but who's more famous for his work in statistical physics. So on that note, I'd like to welcome you all, and I would like to introduce the talk by the man, the legend, Sir Roger Penrose.
Well, thank you very much for that introduction, and thanks also for that medal. I wasn't expecting that. And it's a great pleasure for me to be back in Slovakia. I say back, I was here, I don't know here exactly, but I was in what used to be Czechoslovakia, but it's the part which is Slovakia, so I guess that's okay. In 1962, when I was at a conference in Warsaw, and I drove back through the country. So anyway, it's a great pleasure to be back, and I hope I can live up to all the comments that we made. Now I want to say something about cosmology, and let me get my things in the right order here. Excuse me. I apologize for using this ancient technology, but I have to know where I am exactly. So let me, can I draw? No, I probably can't draw on that. I should know where I am, so I put this in the right place. Okay, so I want to be talking about something which I refer to as Hawking points. Now, to explain what they are, I shall begin by talking about the universe. And the universe, here's a picture of it. Well, it's a cartoon, I suppose. That fits quite well. In this picture, time is going up the picture, and space goes this way. Of course, I can't draw all 4 dimensions, so you have to imagine that the 1 dimension of space this way is really 3 dimensions. But that's all right, you can get used to that idea. I hope you can hear me adequately. Okay, I hope that works. It doesn't work. Does this work? Well, When I hear silent, oh, that. That works. Good. Well, this is a picture. This is a picture of the universe, and this is time going this way, and you must think of sections through this as being space. I can only, of course, draw one dimension of space, but you have to imagine there are really three going this way. You might ask what all the frilly stuff is the back doing. Well, that is, we don't really know whether the universe closes up or whether it keeps on going. Most cosmologists think it keeps on going. Maybe it does, maybe it doesn't. That doesn't play an important role in what I want to say, so you can imagine either way. So the universe starts, expands out, and it's now doing this accelerated expansion, which people call due to dark energy. I don't like the term dark energy because technically it's neither dark, it's invisible, nor is it actually energy. It behaves in a different way from ordinary energy. It is consistent with this term that Einstein introduced in 1917. He introduced the general theory in 1915, and a couple of years later he introduced a thing called the cosmological constant, and the letter lambda, the capital letter lambda, is often used to describe this constant. Einstein introduced it, unfortunately, for the wrong reason, because he wanted a universe that was static, not expanding, and it became pretty clear after the observations of Edwin Hubble showed that the universe is pretty convincingly expanding, and so then Einstein retracted his model. He also retracted lambda and said that was his biggest blunder. He's quoted of saying that this was his largest blunder, but in fact it turns out that even his blunders are true, and this particular blunder seems to be actually a feature of the universe. Now, some of you who are experts in cosmology will tell me there's something missing in my picture. There's supposed to be this thing which took place right at the beginning called inflation. Now, you see, maybe I have depicted it in my picture because inflation would be right inside that little black spot, and you would not know if it was there or not. It's supposed to be an expansion. I should explain that there are two reasons that's not in the picture. One is that it maybe is in the picture, in that little spot. The other is that I don't really believe it. Now, that's a pretty heretical thing to say, because inflation is part of current cosmology. It's a very foundational part. And in order to get some idea of what this little spot looks like, we need a very powerful magnifying glass, which we will see what we'll see, and what we see is something like this. I should explain that's the handle of the magnifying glass, not some feature of cosmology. But what we have is an expansion which looks pretty well like what we see now, but on a completely different scale. This is right at the beginning, a tiny little event expanding by an enormous amount, and now we seem to see an expansion. It's called an exponential expansion, which means that it's self-similar, that is to say, it's how big it is at any moment, the expansion rate goes with the size of the universe. So it's an exponential expansion. Okay. Now, if you don't believe inflation, then you have to have some other explanation for certain observational facts. One of them, the one that's most popularly described, is that somehow this inflation irons the universe out. You see, it's pretty uniform over all directions, pretty uniform, not altogether, but pretty uniform. And this is a bit of a puzzle. We'll come back to that later on. But one of the explanations is that this inflation which took place here, sort of any irregularities will get ironed out by this inflation. Now, I've never really believed that argument, and let me try and explain why. Let's suppose that the universe was contracting instead of expanding, and the equations of Einstein and the equations of what's called the inflaton field, which drives the inflation in the theory, are completely reversible in time. So if that's a solution with the inflation, say, then this is also a solution. So these things are, the laws are completely reversible. Now let's imagine that the universe was contracting and that it had various irregularities. These irregularities would tend to build up, form black holes and things that get tangled with each other and make a great mess. and you would have one horrendous mess at the end. That's the likely thing that would happen. Now, if that's a likely thing that would happen, why didn't this happen? I should explain that you can put the infraton field, which is supposed to drive inflation, just as well in this picture. It makes no difference to the picture. So that is a really much more likely thing than this. And in fact, you can give a measure to the improbability of this, which is what we seem to see, as opposed to this, inflation or no inflation. And just to give you a feeling for that figure, the improbability of this you have to think of as 1 in 10 to the power, that is to say how many digits it's going to be. How many digits is that? 10 to the power of 124. I used to say 123. 124 is just to include dark matter. It don't matter. It doesn't make any difference to the argument. Absolutely enormous difference to the figure, but it doesn't make any difference to the argument. So why did our universe start like that and not like some horrendous mess like that? Well, I'll come back to that issue because that's important in what I want to say. But in order to talk about this, I want to do a couple of mathematical tricks to the universe. One of them is to squash down infinity. Now, to give you a feeling for what that is, I have a picture here. The Dutch artist M.C. Escher produced many wonderful pictures, very, very accurately as mathematical pictures. This is a picture describing what's called hyperbolic geometry. It's a particular kind of geometry, not quite like the Euclidean geometry we're used to, but it's fairly similar. And you have to imagine that these fish creatures, even though they look as though they're getting smaller and smaller as you get to the edge, to them, they're just the same size. So they're squashed down in this representation in a way which is what's called a conformal representation. That's to say that the squashing in one direction and any other direction is by the same amount. So little shapes, when they get squashed down, remain the same shape. And you can see that particularly with the eyes of the fish. No matter how close to the edge they are, there's still circles. So they're squashed just as much one way as the other. This is what's called a conformal map. And the advantage of the conformal map is that you can represent the infinity of the world that these fish inhabit, and that infinity is represented by the circular boundary to this picture. It's just a convenient way of representing the entire hyperbolic plane in a finite way. And this little trick is the same as I'm using here. I'm using the trick to space-time geometry rather than just a spatial geometry, and I'll come to that in a minute if I can remember how my slides work. Yes, that's it. Now, there's an opposite trick you can do, and that is to stretch out the Big Bang. So it's again one of these conformal maps, but in the other direction. This is all squashed down to something small, and you can stretch it out. Now, all the standard cosmological models that people use in general cosmology, you can do this trick too. So those two tricks, there's nothing unconventional about that. It's a perfectly reasonable thing to do, and it's useful to do these mathematical transformations if you want to talk about things in the remote future, or if you want to talk about things going on in the Big Bang. It's a very handy thing to be able to do these tricks. Nothing unconventional. Now, what I'm just about to tell you is unconventional. That is to say that the universe we think is the whole universe, that is to say, in my previous picture, the Big Bang right out to the very remote future, inflation if you like, and this is not, in my view, in the view I'm trying to express here, it is not the entire universe. It is one eon. I'm using the word eon. I looked up in the dictionary to find out how long an eon was. Fortunately, there is no definite length of time, so I thought it was all right to use the word eon, A-E-O-N, is the way I spell it anyway, and that is what I call this entire history of this thing which we used to think, or most of us still think, that I used to think, is the entire history of the universe. Squashed down like this, and stretched out like this, and our Big Bang, then, is the continuation of the remote future of a previous eon. Our remote future will be the will continue into the Big Bang of a subsequent eon. And the thing is, in order to make this picture, which I now have on the right-hand side, to make that picture make physical sense, you have to understand that the physics at both ends can be reasonably thought of as conformally invariant physics. That is to say, physics where it doesn't matter whether it's big or small, that the universe in some sense loses track of how big it is. That's a difficult thing to swallow, and I know most cosmologists have a lot of trouble swallowing it, but I want to explain certain things which I think are hard to explain in any other way than the picture I describe here. These are pretty new, just last year, things I want to talk about today. So it's taking people a while, I think, to come round. Whether they will eventually or whether they'll shoot me down, of course, is another question. But let me try and explain on the physical terms what the conformal mappings do. You see, this is space here, but when you've got space and time together, then what we have to think of, the best things we think in terms of, are these things called light cones. Now, what's a light cone? You see, think space-time is four-dimensional, time is one of them, space are the other three. In my pictures, I'll either throw one space dimension or two away just to be able to draw the pictures. Now, what are the light cones, or null cones, technically? Here's a picture of one. That is a point in space-time, that's an event. That means it has no spatial dimension and no temporal dimension, so it's just a blip like that. And this event, then what is the cone? Well, that represents what light would do. So the history of a light flash from then outwards would be described by this cone. So you have to imagine, as time progresses, we take sections up and up and up and up. Of course, I've thrown a dimension away, but never mind. So that thing that looks like a circular section is really a sphere as time progresses. Is there something funny going on here? Oh, yes, thank you. Yes. Can I draw? I can draw on this, I guess, can't I? Draw whatever you want. This is a cloth, though. I don't want to draw on the cloth. Let me draw on this piece of paper. Let's hope that will tell me where I am, more or less. I'm sorry? You want it higher? I didn't hear it. It's backwards, is probably what you're telling me. Is that it? I have to apologize, I can't see what I've written. My eyesight has deteriorated, so I appreciate when you yell at me that there is something wrong. It's probably I've got the slides upside down. Thank you very much. Okay, now this is a light cone, and it's the most important part of the description of space-time, is the cones. They tell you, it doesn't tell you there is a flash of light there, it just tells you if there was a flash originating there, then it would describe this thing called a light cone, or locally what we call a null cone. Now, there are a couple of things I want to say about this. First of all, well, light, that's the history of a photon, say a particle of light would go along here. So now, think about this picture here. I should explain that the structure of space-time is described by what's called the metric, or the metric tensor. And the metric tensor is a thing which at each point in space-time requires 10 numbers to tell you exactly what's going on there. Those 10 numbers, 9 of them, roughly speaking, tell you where the light cone is, or exactly how it's structured in relation to space-time. When I say 9, it's really the ratios of these 10, the 9 independent ratios of the 10 numbers. What does the remaining number tell you? It tells you how clocks behave. So here we have a picture of a couple of clocks zipping by, very close to each other at this point, and the ticks of these clocks are represented by these surfaces here. Now, a point about clocks is people often used to describe relativity theory by imagining a lot of little rulers all over the place and measuring distances. Rulers are now no good. They're lousy at measuring distances. They're not the way you measure distances anymore. The meter rule in Paris, well, nobody would go, no physicist would ever go and use that to measure an actual distance. What they would do is have a notion of a clock and then use how long it would take light to go that distance. So you convert distances into times using the speed of light. Now the thing about times, that they are now devices which are so extraordinarily precise that, well, I think if you, I don't remember the figure now, but if you had clock right at the Big Bang, and it was could keep time in the way of clocks we have now, then we would know the time. Well, it's a rather bad description because you don't know exactly when the Big Bang was, so that but to some tiny fraction of a second. The precision in the clock is that great. Or another way of putting it, clocks are affected by the gravitational field, and according to Einstein, a clock runs slower. The clock runs slower down here than it does up there. And the difference between those rates can be measured even just about that distance. So from here to here, the difference in the rates of the clocks go can be actually measured. It's extraordinary how precise they are. And the precision really ultimately comes down to two of the two, I should say, most fundamental formulae of 20th century physics, or the two most familiar ones, if you like. One of them, of course, is Einstein's E equals mc squared, which I've written down here, which tells you more or less that energy and mass are equivalent. Oh, if you've got the c squared, but that's just a constant. So energy and mass are equivalent. The other one is Max Planck's formula, which came a bit earlier, E equals h nu. I don't know whether you like to use a nu or an f or something. That stands for frequency. So it tells you that energy and frequency, h again is a constant, so it's telling you that energy and frequency are equivalent. So you put the two formulae together, energy and mass are equivalent, energy and frequency equivalent, that tells you that mass and frequency are equivalent. So if you have a stable particle of a given mass, it is a clock. It's a clock of extraordinary precision because of those very basic rules. You can't necessarily use that precision directly, so you've got to tone it down and use lots of particles and all that sort of thing, and all sorts of detailed things to make an actual clock. But the reason that it's so precise is because we are using those two very fundamental laws to measure the rate of time. And so time can be measured that precisely. Okay, so we have now the 10 components of the metric. 9 of them give you the cone, and the 10th one gives the crowding of these surfaces, which tell you the rates of different clocks, how they would tick. First tick, second tick, third tick, and so on. And this is them coming in from the back, first tick, and so on. So that's the picture you have. Light cone is more fundamental. If you have mass around, you see the other end of the story, it's not just that mass gives you clocks, but if you don't have mass, you don't have clocks. This is the key point. Now let's imagine you have a photon. Now that's a particle of light. It zips along the cone. It never even reaches the first of these surfaces. To a photon, there is no time whatsoever from its origin to where it ever gets. There's no experience of time by a photon. So that's a remarkable fact about the way physics works. And here I have a picture now of, I hope I can get that up there. There we go. Here we have light cones. They can be sort of this way and that way. Here we have a light ray following the light cones. That's fine. That's a photon. Material particles, they're not allowed to go as fast as light, according to theory, and so therefore the world line of a material particle, that's the track of that particle through space-time, is always within the cones, like this. Now you can have funny things like black holes. Here we have a collapse of some material, produce what is a black hole, and you see that the cones are all tilted over so that signals can't get out from here outside, but stuff can get, there's this thing called the singularity in the middle, which is bad news if you get close to it, but you can see the cones point inwards more and more and guide whatever falls in towards the central region here. So you have a picture of a black hole, and you have the basic feature of space-time, namely this light cone structure. Now you see, if you have massive things around too, so they can actually measure how clocks tick, then you need a bit more. So these are I put the little bowl-shaped surfaces and hill-shaped surfaces this way to represent the crowding of them tells you the rate at which clocks go. So this is the picture that you really need for Einstein's theory. This is what you need for the conformal theory. Now you see, if you didn't have any mass, this picture would be good enough. If you have mass around, then they determine clocks. So I want you to get the feeling of the difference between these two situations, because it's important for what I'm trying to say. Now let me go back to my picture of the universe, which I've squashed down infinity and I've stretched out the Big Bang. Now you see, what's going to be around in the very remote future? Well, almost entirely photons. The particles will be almost entirely photons. And photons aren't interested in escape. So as far as a photon is concerned, this boundary is as good as anywhere else. And the other thing to bear in mind is that there's a lot of matter running around, but where it's liable to end up is in black holes. You see, we, in our galaxy, in the center of our galaxy is a black hole. Observations, very clear on this. A black hole which is about 4 million times the mass of the sun. So 4 million suns compressed into this tiny region. And you can see, it's very impressive to see this almost in real time, not quite real time. You can see stars going around this object. You can't see the black hole, but you can see the orbits of these stars, and they follow these Kepler orbits. You know, you have to take photographs, I don't know, how weeks apart or something, but you can actually track the actual motion. So we know there's a 4 million solar mass black hole in the center of our galaxy. Now, what will happen to that black hole eventually? Well, it grows and grows as it swallows things. Clusters of galaxies, we're in a rather small cluster. We have the Andromeda cluster and the Triangulum, or whatever the other one's called. And we're pretty small, but there are much, much bigger clusters out there. Clusters, as the universe expands, they tend to hang together. And so the black holes will sit there for a while, and every now and again they'll run into each other. You see the Andromeda galaxy is is another member of the cluster that our galaxy is in, the Milky Way galaxy. And we are on a collision course with the Andromeda galaxy. Well, it's not a dangerous thing. Even when they hit, it's probably not dangerous. But it won't be for a few thousand million years, so don't worry about it. But this black hole is I forget the figure, 40 times bigger than our one. So it's a lot bigger than ours. When the galaxies collide, the black holes will undoubtedly miss each other, but they will gradually feel each other out and spiral around into each other, and then there will be some great explosion of a kind which I'll say something about later on. Gravitational waves will carry the energy. A considerable proportion of the energy in that collision will get carried away. But nevertheless, in a cluster, it will end up with one big black hole, a lot bigger than the Andromeda one probably. There are a lot bigger ones seen in other places. When I say see, you don't directly see them, but you see the effects of black holes. And these black holes, there are some a lot bigger than the one in the Andromeda galaxy. So you get absolutely huge ones, and I don't know what the figure about this is, but I would guess that the majority of the actual material in the cluster of galaxies will eventually get swallowed by this ultimate black hole. So bear that in mind, because that has a lot to, will feature in what I want to say later on. But then, you see, this picture is illustrating something else. This was Stephen Hawking's greatest contribution, was to realize that although black holes swallow things, and they swallow radiation and so on, they actually have a temperature. They're not exactly cold. Now you might ask, how hot are they? Well, the smallest ones are the hottest ones. And the smallest ones, well, they're probably a few times the mass of the sun. And those ones, well, just to give you a rough idea, how hot are they? Well, you have to think of something like the coldest temperature ever made on the Earth. I'm not sure if that's quite right, but something like that. And you get some idea of how hot they are. Not hot, in other words, very, very cold. The bigger ones are even colder. But as the universe expands and expands and expands, the radiation in the universe will eventually get smaller, by this exponential expansion, smaller than even the biggest of the black holes. And then the black holes will be the hottest things around. Now I remember the origin of this crazy scheme which I was describing to you here came about because I was worrying about our universe. I don't know why should I worry about the universe, but I was worrying about the universe, thinking about the incredible tedium of the whole thing. You see, what's the most exciting thing that will be around in the very, very remote future? Well, black holes. And what happens to them? Well, the biggest ones will take something like a googol years. That's 10 to the 100 years. 1 with 100 zeros years. That sort of length of time, or longer, probably longer. That length of time they will take before they evaporate completely away and disappear with a pop. I'm calling it a pop rather than a bang, because even though there's a fair amount going on just before the end, these explosions from an astrophysical point of view are pretty trivial. And you have this huge black hole sitting around, you wait, you Google years, 10 to the 100 years or something like that, and eventually. Now what could be more boring than sitting around waiting for a black hole to go off pop? What's more boring is what happens after that, when there aren't even any black holes left. And I began to think, it's a pretty depressing thought that the future of this wonderful universe of ours is eternal at tedium. And I began to think, well, who's going to be around to be bored? Well, not us, but at least the main things that will be around will be photons. And it's very hard to bore a photon. You see, I did explain, not only do they probably not actually have any experiences, that's not the point, but you see the photon zips along the light cone, and it doesn't have any experience, in that sort of generalized way of saying experience, any experience of the passage of time. So right from, you can imagine this picture, it just zips along and goes right through what hits the boundary at what, as far as it's concerned, is a finite time. So this is what the sort of picture I was having here, was this picture here, and worrying about, well, maybe it's not so boring because the photons and things will have somewhere to go in the picture which I've been trying to describe for you, which I've gone and lost now. Find it. Here we go. This picture, they find themselves into the next eon. So, okay, that's an emotional argument, and I grant you it's an emotional argument, but it has something important to say about the universe, which I'll come to shortly. I should say, first of all, that there are mathematical theorems. The one most particularly I refer to here is a theorem due to, let's make sure I get this the right way up, a theorem due to Helmut Friedrich, who showed that under very, very general circumstances, let me make sure I've got the right one, yes, under very general circumstances, this smooth future boundary will be there. So you don't have to worry about crinkles and things like that. It will be nice and smooth and a nice place to go here. It's completely different from the beginning picture, because I showed you this most likely situation, much more likely than what we seem to see, is a universe which is a great mess. So the likely, if you just chose at random an initial state at the beginning, and I'm just drawing these pictures here, it's much more likely to have been that rather than something which stretches out to make a nice, smooth, original boundary like this. Now, why is this important for us? Well, it's important because of one of the most fundamental laws of physics, which is a thing called the second law of thermodynamics. Now, what does the second law of thermodynamics say? Well, there's a thing called entropy, which, roughly speaking, is a measure of the randomness of the situation. One could be technically more accurate than that, but think of it as that. The randomness of a state is measured by its entropy. And the entropy increases with time. That may be a depressing thought, but it's reasonable physically that it gets more and more random as time goes on. Well, that's, not a thing that one would necessarily disbelieve, because, anyway, there's a lot of evidence for it. But let me say it in a different way. Rather than thinking about going into the future, let's think about it going into the past. Now, the same statement, the second law, is saying that as you go back into the past, the entropy goes down and down and down. It goes down and down and down until, well, what do you find? What is the best evidence we have of the existence of the Big Bang? Well, it's this thing called the microwave background, which was just a bit over 50 years ago, was discovered sort of accidentally, but it's radiation coming in from all directions. And there are certain features of this radiation which were found by the Kobe satellite, the main one being the following. I'm going to give you a curve here. What is that curve? Well, this curve, the brightness of that Probably with this picture, I'm not sure. This curve is a measure of the intensity for different frequencies. The radiation is electromagnetic, like light and radio waves and X-rays, that kind of thing. And it's what's called microwave radiation. And this is for different frequencies, you see different intensities. And what you see is this curve here. Now, what's the importance of that curve? It's a very, very precisely seen curve. I should say that there's a theoretical curve, that's the black line, and the observational curve, well, these are error bars, you see. That means that's the possible error in the observations. And you see they're quite big here, but they're not really big because these lines are exaggerated by a factor of 500. So you've got to imagine the real error is 1/500th, even where they're the worst down here, they're still hugging that incline. So the observations hug this theoretical curve to within the thickness of the incline, much less than that, in fact. So what does that tell us? Well, this is the famous Planck curve, which started off quantum mechanics, Max Planck, beginning of the 20th century, and you see this very precise curve. And what it's telling you is maximum entropy. Now you see, I regard that as what I sometimes refer to as the mammoth in the room. Because you're going back and back in time, the entropy is supposed to go down and down and down, and what you see at this early stage is apparently maximum entropy. You're going down and down and down until you reach a maximum. You don't have to be a mathematician to think there's something fishy about that. Well, some people might say, well, it's something funny about the universe expanding, and maybe that's the answer. No, it's not. And a cosmologist known as Tolman, who was around at the time of Einstein, perfectly well understood these things. No, that's not the explanation. But what is the explanation? Well, what we're seeing here is matter and radiation apparently at this maximum entropy state. But it doesn't tell you that everything is at a maximum entropy state. The important thing it does not tell you is gravity. Now let me give you a picture here where I try and explain what I mean. Here we have, this is the sort of picture that people talking about entropy often give you. Here we have a gas in a box, and you imagine that the gas starts off by being, there's a partition here, and then you release the gas, and as the time progresses, it spreads out over the box. So you have a picture of entropy increasing as the gas gets more and more uniformly distributed. And this is consistent also with the microwave background, because not only do you see maximum entropy here and here and here and here, but you also see very great uniformity over the whole sky. If you take into account the fact that the Earth is moving through this radiation, so it's slightly hotter in the direction in which it's going, and slightly colder in the direction, I don't know which way it is really, but the direction we're going is slightly hotter, and the other direction is slightly colder. You correct for that. And when you correct for that, you find that the temperature variations over the whole sky are something like 1 part in 100,000. So it's pretty uniform over the whole sky. So you're seeing something which looks like this still. But when you think about gravity, now you see here I've got a picture. You must imagine this is sort of a galactic scale box, and these are stars running around in that box. And with gravity acting on those stars, these stars tend to clump, you see. So, or it could be stars, or it could be gas, or something like that. And the tendency for gravity is to clump it. And what you have is entropy increasing in both these pictures, but what we seem to be seeing is uniformity. Now, as far as gravity is concerned, that is low entropy. So I put my pen here, and you see that these two pictures are consistent with what we see. As far as matter and radiation is concerned, yes, it's very high entropy. But this is completely compensated by the fact that with gravity is concerned, well, it tells us that the entropy is extremely low. And in fact, in this picture, I've got entropy increasing, until we have a black hole. And a black hole represents an absolutely enormous entropy. So in fact, in the universe that we know today, as far as we can see out, the maximum entropy in the universe is in black holes, by far. by an enormous factor, the entropy in black holes, even now, is far greater than in anything else we see. And that's going to increase as time goes on. As black holes run into each other, the entropy will go shooting up. So it's not inconsistent. It's not a paradox, this picture. What I'm telling you is what it's telling us is that the lowness in the entropy in our universe, the thing that drives the second law of thermodynamics, is gravity. And it's something very special about the early universe. And what I find very puzzling about this is why cosmologists don't worry about it more. Not just the fact itself, why was gravity so differently treated than everything else? The other puzzle about this is why, as I say, cosmologists don't seem to worry about it. You often see lists of what are the remaining puzzles about cosmology, and they list all sorts of different things. Where is the fact that the universe seems to be so low in entropy, in the gravitational field, and not other things? Well, you see, I don't see any other scheme of cosmology which addresses that question other than one I'm showing you here. So that's one of my main reasons that I should have been spreading these things out better, so I don't lose them. But here we have our picture, and if you try and find my... I'm sorry about this, in here somewhere. Well, I just want to go over something. Let me just say, while I'm searching, something else about this. You see, it's really what drives everything about, I mean, why are we here? You see, we're sort of centers of low entropy, each one of us. Where does that come from? Well, ultimately it comes from the sun. And the sun is a source. People often say it's a source of energy, but it's not really a source. This is a point made by Schrödinger, and he got into a lot of trouble for being correct on this one. And I say he was correct. He said that basically we don't get energy from the sun because here is the sun, and we get photons coming from the sun, and they just go back. In the night, they just go back again, you see. So you get as much energy coming from the sun as goes out. Well, global warming, I suppose, means a little bit more gets caught here, but that in this picture is much less than what I'm telling you here. But the energy going out is about the same as the energy coming in. But what's different is that the energy comes from the sun in much, much hotter individual photons, and it's visible, blue or yellow or something, photons coming from the sun, and those going out are infrared. These are much less energetic individually, so you need many, many more of them going out to carry the same energy. So you have a relatively small number of photons coming in and a relatively large number going out, and that's what the plants make use of, and that's what animals make use of, and what we make use of when we eat plants or animals or whatever it is, and that's what keeps us going. That's what keeps our entropy low, is the sun being a hot spot in a dark sky. And that comes about because, well, there are nuclear forces and so on important in keeping the sun going, but the main thing is that it's there at all, and it collapsed out of some gas that was out uniformly spread, and then as it clumped together, the entropy went up. But there's a big, large reservoir in the uniformity of the matter, which is what this whole process is making use of. So we need to understand that the key problem is to understand why the universe was so uniform and therefore so low in entropy, in gravity, and not in other things. And I must find my picture again, otherwise I shall not be able to say what I'm trying to say. Ah, no wonder I could find it. Thank you so much. It did slip on the floor. Yes, there we go. So there's my picture. Now you see, I hope that's all right. Roughly speaking, the picture only works because the initial universe was nice and smooth and was not this horrible mess, which, as I say, was much more likely. The likelihood of that initial situation, as opposed to the very smooth one, as I said before, is 1 part in 10 to the 10th of 120 4 or something like that. So we see not that, but we see this. Now you see, I spent a lot of time in my earlier days trying to characterize the Big Bang, and I came up with a thing I call the Weyl curvature hypothesis. That's a bit difficult to explain. I'd have to tell you what Weyl curvature is. My former student and current colleague, Paul Todd, came up with a much better way of saying it. What he says is the condition on the Big Bang, for whatever reason, is that you can stretch it out to make it something smooth, like this. It was just a mathematical statement. He said, okay, that's a nice way of saying what we mean by the universe having low entropy in the gravitational field. It's a nice geometrical way of saying it. And I think it was much better than my way of saying it, so I'm going along with his way. And more or less what his way says, that you could, if you draw this conformal picture, that you can extend it smoothly into something before it. Now, he didn't say what it was before it. He just said that's a nice mathematical way of saying how smooth it is. But what I'm saying now is, yes, there was something before it, and that was the conformally squashed down infinity of the previous eon. Some people might worry that the Big Bang was hot and very dense, whereas the future is very cold and very rarefied. But you see, when you do this conformal thing and squash it, it has this effect on energy and momentum and so on. That means hot, when you stretch it out, becomes cold. Cold, when you squash it down, becomes hotter again. And so that all makes sense. So as far as the physics is concerned, joining this very hot thing onto this very cold thing, as long as you're looking at physics, which doesn't have any mass, you see, going back to this earlier picture, where I had the universe with just the light cones, and that was that one there. That's the physics of massless things. That's to say, without any mass, they don't weigh anything. And this is the physics when you actually have to take mass into consideration. The equations of Maxwell, which describe how light behaves, have the property that you can stretch or squash. You can squash here and stretch here. They work just as well. This is also true of what are called the Yang-Mills equations if you regard them as classical equations. Don't worry about quantum mechanics, and you wouldn't worry about the mass of particles involved. As long as you're just looking at those forces, again, it's true, apart from quantum mechanics, things to worry about. Classically, it's just the same as to say stretching and squashing, you don't notice the difference. It's things with mass that do notice the difference, and that could be mass itself, or it could be gravity, because the source of gravity is mass. So when you're talking about Einstein's general relativity, you've got to be a little careful, because that is not invariant under removing the scale. So that's something you do have to bear in mind. Okay, so that's the picture. And, well, two questions. And some of you might worry, quite reasonably, that if you've got a theory in which, like this, you've got, let's say, a cyclic model where things overall don't change very much. Each eon is supposed to be, roughly speaking, not in detail the same, but roughly speaking, overall the same as the eon before. Now, how does that square with the second law of thermodynamics? Because the entropy is going up and up and up, up and up and up, up and up and up. How do you make sense of that? I may say that worried me for quite a bit, and I thought there was some little catch about phase spaces and things like that. No, that's not the argument. But you see, the things that I'm saying here are not, I should say, totally accepted by people. I hope they will be eventually. But the point I was making is, I made it a while ago, that the major contribution to the entropy in the universe is in black holes, by absolutely an enormous factor. And remember, what happens to the black holes? Well, they eventually evaporate away. But what happens to the entropy? What happens to the information in the black holes? Well, here I have to appeal to one of the two Stephen Hawkings. Now, when I say two, there was a Stephen Hawking who initially put forward his theory of the black holes radiating away, and he, at that time, said that information is swallowed by black holes. It's lost in black holes. He then, in a later time, changed his mind and said, no, the information somehow must come back again. Okay, you can take sides on that. I think he was right the first time. And I think the evidence that he was right the first time is pretty strong. I know a lot of people argue the other way, and even, well, I would think probably most physicists who think about this think the other way around, that information must be regained. Well, that's because, the main reason they think that is because there's a fundamental principle of quantum mechanics which tells you, it's called unitarity, which basically one of the things it tells you is that you can't lose information. It's got to be there somewhere. But unitarity is something which is violated by the way we use quantum mechanics when you make measurements. So you have to worry about this, and that's a long story which I don't want to go into here, but I think one can make very cogent arguments that information is lost in black holes, as Stephen said, and it's very crucial to this picture that it's lost. And as I said before, that's where most of the entropy is in the universe as we know it now. And so when those black holes disappear, the effective entropy comes down. Now the thing is, it's a little bit subtle here, because the entropy is not a violation of the second law. You see, the second law of thermodynamics says that the degrees of freedom will get more and more thermalized as time goes on and so on. That's okay if you keep track of all the degrees of freedom. But if they get swallowed up by a black hole, you've got to start again and say, do we consider those degrees of freedom to be important in our calculation of entropy? If you say, yes, we do, then the entropy is still going up. If you say, well, look, I'm not interested in those anymore because they've gone down the hole in the black hole, and so they're gone. So then you've changed your mind about what you mean by entropy. And so it's that change of mind, it's quite a subtle thing, that's change of mind which allows you to say there's no violation of the second law here. Because as you get close to the crossover between each eon and the next, then you have to decide what to do with your definition of entropy. You say, well, let's forget about all those black holes, they're gone, the information has been lost in them, and therefore what we use to measure our entropy has gone down. It's not that there's any violation of the law, it's just that what we regard as the entropy of the universe, you've changed your mind about what it is, or you renormalize it. That's a term that physicists will like. Anyway, so that's the first point I want to make. The second point I want to make is this scheme true or not? Well, I gave lectures on this for a long time, thinking it didn't matter. You know, I would never be contradicted because nobody would ever know. But then I started to think of possible observational tests, which is a little disturbing because they might turn out to be in disagreement with this theory, or they might not, which is troubling both ways, never mind. But let me explain the first idea I had. That's not the main point of this talk. But the first idea I had was, I mentioned, you see black holes running into each other, swallowing each other up, getting bigger and bigger and bigger, and then evaporating away. So what happens when they collide with each other? Well, there is a lot of radiation coming out in the form of gravitational waves. If they went through this room, you probably wouldn't feel a thing. They don't disturb most things. Nevertheless, they would come up to the crossover surface. This picture here, this is supposed to be the eon prior to ours is down here. Our eon is here. That's us here looking back. That's our past light cone. That's what we see is information coming from here. And these are some black holes running into each other. Bang, bang, bang. These are gravitational waves. And these gravitational waves cause signals that we should be able to see. Now, I'm not going to talk about these signals here, although there does seem to be good evidence that they are there. I have an Armenian colleague, Vahe Gozadjan, and we wrote a paper which seemed to see pretty evident that they're there, mainly because they're so ununiformly distributed over the universe, which is hard to explain any other way, but these signals, I should say. The other is by a Polish group headed by Krzysztof Meissner in Warsaw, and they, in their first examination of the WMAP data, which was a satellite which looked at the microwave background and details of it coming in all directions, and they analyzed the data and came to the conclusion that the signals are there with a likelihood or a confidence level of 99.4%. Okay. I think it's 99.4%. But subsequently, there were some other observations, and that's really what I want to talk to you about. It was part of the whole program of looking for these signals, and this is something completely different. Although it still has to do with black holes. See, I have two pictures here. This one is to do the black holes colliding with each other and these signals coming out, which I claim there is pretty good evidence that signals are there. I've never heard an argument which contradicts, particularly what the Polish people have seen, and they're at 99.4%. They say, well, maybe it's a chance effect or something. But if it's a chance effect, the probability of it being a chance effect is only about 1 in 124. So it's much more likely to be a real effect, but people have not paid attention to that in cosmological circles. But here's something else. And I had thought about this before, but it disturbed me, and so I didn't think about it much more. What about these black holes, these huge ones, which have swallowed up most of the matter in a galactic cluster? And they're sitting around there forever, well, not quite forever, for 10 to the 100 years or something like that, or longer, probably longer, the really big ones. And they sit there, and they sit there, and then they gradually evaporate away according to Stephen Hawking, and I'm agreeing with that. I think that's completely right. They will evaporate away. What happens to all the energy in that radiation? Well, first of all, it's extremely cold. That radiation, if you had, you felt it from it ridiculously cold, as I was saying before. But nevertheless, you've got an enormous length of time with all that energy coming out and concentrated. And now again, I've got to find a picture of it. I'm going back to my Escher picture. I hope that's not on the floor. I think things tend to run on the floor, so... Oh, there we go. I think this is a useful one to think about. You see, of course, this is not quite a space-time geometry, but nevertheless, as you get very close to the edge, then the radiation coming out will be concentrated in that little tiny spot. So even though it's a very low intensity, it's all squashed down into a little tiny spot. So the entire mass energy of that vast black hole, which has swallowed up all these stars and things in that huge cluster, will be burst through there. And it will come through, according to the scheme. You see, here we have the crossover surface between the previous eon and ours. What have I drawn here? Well, this is what's called the last scattering surface. You see, when the microwave radiation is produced, the thing we see, this radiation coming from all directions, which I talked about before, that didn't come really from the Big Bang. It came, well, about 380,000 years after the Big Bang. That seems to us quite a long time, but cosmologically, that's quite a short time. But it means that the energy coming in here, if this picture is correct, was spread out to about 4 degrees in the sky. How big is that? Well, the moon is about half a degree, so 8 times the diameter of the moon. So these individual points, these are what I call the Hawking points, because this is the Hawking radiation concentrated in that little point, and then it spreads out to a much more uniform distribution. But I should say the temperature variation that we see in these spots, I should say we see the spots, if that's what they are. We see these spots which are of that sort of size, and that's one of the critical things, that they're not bigger and they're not smaller. They could be a little bit smaller because when we look back, we may just sort of catch the edge of it. So maybe from about 2 degrees across to about 4 degrees across. You should see, according to this theory, the spots, which would be the radiation spread out from Big Bang to 380,000 years afterwards to what we actually see in the microwave background. Now, how much is the change in temperature there? Well, I mentioned that the temperature variations you usually see, that's the normal things that people see, are about 1 in 100,000. So that's pretty small. This is about more than 10 times as much. So you see a variation in temperature which is a lot more than the general amount you see. Why haven't people seen these before? Because they haven't been looking. There seems to be a view that the universe ought to be very uniform, and they don't bother to look for things like this. You have to be a bit careful, because the analysis that was done, I should say this is a paper which is on the archive now, by Christoph Meisner, Daniel Ahn, he's a Krzysztof Meisner is Polish, Daniel An, who is a Korean and works in New York, who's actually done the detailed analysis of the, this is called the Planck satellite, of the information from the Planck satellite, and Paweł Mirowski is another Polish person. They've all been working together on this work. Now, what we seem to see, and I shall give you some figures here, although I don't want to say too much about it. I think, first of all, I'll show you this picture here, which is what we seem to see. See, this is the black hole. It swallows all the cluster up, so it's absolutely hugely massive. And then eventually, just underneath here, it spreads out to about this big bang. The Hawking point is there, and then it spreads out to this size of about 8 times the diameter of the moon, 4 to 8 times, say, the diameter of the moon. And that's what we seem to be seeing. Now, what's the evidence that we're seeing it? Well, I just give you some figures, and there's not much point in going into the details here, but it came about first because Daniel had done. How do you know an effect is real? You see, well, the standard way people do it, you see, we don't know. The trouble is we only have one universe, so if you see something, is this something unusual or isn't it? Well, the way it's normally done, and one can argue about these things, but it seems to be quite reasonable, is you make some kind of a fake sky, which is not the real sky, but agrees with the real sky according to this picture here, which is called the power spectrum. Let me not say about what it is in detail, but it's something to do with the distribution of irregularities over the sky. And you have some overall measure of the distribution of the irregularities, and then you're supposed to feed that in, that you randomize within that constraint. So you use that from the real sky, and within that, you randomize. And then you make zillions and zillions of these different fake skies, and you see how many of them see the feature you're looking for. Well, first of all, Daniel did 1,000 of these simulations, and this is represented by one of these columns here. You see a 0. You see, this is you look at how many of those fake skies see this feature. What did I say? This is. You look for a feature, and these are different sizes of rings and so on. That's what all these numbers are. But if you get the particular size which I'm talking about here, and I guess there are 2 of them which I can roughly describe here. These are very crude pictures, but it's known as this. These are the 2 ones you seem to see in effect. This is, I'm afraid these are in radians, not degrees, but never mind. The 4 degrees across the sky is about that. And these are looking at these rings and seeing whether the temperature goes up as you go inwards. And that's the thing. You see certain points in the sky where this happens, and the question is, how unlikely is it that you see this fact? Well, if you look at all sorts of other sizes of these rings and so on, then you see these big numbers here. Let me look at the right column. Here, that one. You see, that was with his thousands, and then it's down here. And you see big numbers here. These were the number of fake maps which showed the feature more strongly than the real sky. And then you see 0. That means none of them saw this feature at all. So in these fake skies, you don't see this signal. So that means it's probably real. Well, people complained about this and said, well, you've got to do some more, because maybe there's a thing called look elsewhere effect, which means maybe you were looking too carefully then, and maybe, well, never mind. So he did another what was it now? The figures are up here. He did 1,000 and then eventually 9,000 more, so it's 10,000 altogether. Well, you see, for one of these you see 2, and for the other 1, and the numbers have now gone up to the thousands. So this means that if you just look at the probabilities, let me just give you that. What it means is that this signal, well, could be a chance effect, but the chance that it's a chance effect is, well, let me give you a figure. It's a 99.98% confidence level. So that means that one can say that this is a real effect with probability 99.98% correctness. So I think people ought to pay attention to this. If it's not the scheme that I'm describing, and if it's something to do with inflation, well, you see, It's hard to think what else it could be because we understand, I didn't explain this, but we have this curve here, and there's a lot of agreement between the observed and calculations. And what this is basically telling you is that most of the time from the Big Bang until 380,000 years later, the physics is extremely well understood because these things fit so well. So that's very well understood. So it's hard to see how these signals could have arisen after, or say, between Big Bang and 380,000 years. But what about inflation? You see, inflation was supposed to have taken place, well, I use this picture here, after the Big Bang. Now you see, I'm not having inflation. But if inflation were there, then the Hawking point would have to be way down here somewhere. And then the spread would be far more than the spread we see. And it's very clear that you don't see the spread over the 4 degrees. So that's a bit hard to see. They would have to, if inflation was there, the Hawking points, or whatever they are, would have to have been created just when inflation turns off. It's what they call the graceful exit period, which already is a bit of a problem because inflation's got to turn off over the whole universe at the same time, and that's referred to as graceful exit. Graceful doesn't suggest little bangs here, or huge ones, I should say. Enormous explosions taking place in different parts of the universe. We need an explanation. Maybe there is an explanation that comes about from some inflationary theory, and I await such explanation. At least we see an explanation on the scheme which I've been describing today. Thank you very much.
Thank you very much for that very inspiring talk. We have some time for questions from the audience.
I am Jan Rudit, very impressive professor. I have just quite a naive question. Because of second law of thermodynamics, what would be the future of the universe? It's another Big Bang?
Future?
The future of the universe.
Well, the picture I'm presenting says that the universe, our eon, will go on expanding, get more and more rarefied, the black holes disappear, get more and more boring, but then that comes to the next eon. And so it's not boring to things which don't have any mass, because they don't experience that time. So when you say the future of the universe, do you mean each eon, or do you mean the whole picture? The whole picture just goes on and on and on. So, I mean, you could have other views. You could say, well, it stops somewhere. Or you could see these eons change radically in some way. All sorts of things. You can even have it turn around and they can join on, and you can imagine the sort of loop that goes back there. Okay, I'm not saying any of those things. I'm saying, at least my model is that it goes on indefinitely. So the future of the universe, in the sense of eons, they'll just be continuing eons, like ours. Of course, that's just a hypothesis. Maybe something else happens. Maybe they change in some way. All sorts of horrible things can be thought of. I'd like to think of the simplest model in accordance with the scheme, and that is that they just continue indefinitely into the future.
Any other questions?
Good evening. In your cyclic model universe, is there a way how to say in which cycle are we now, or how many cycles have there been so far?
Well, again, that's a sort of another version of the same question. If you go back in time, was there a first one? Well, according to the scheme, there wasn't. The eons continued indefinitely. I mean, only putting this forward as the simplest hypothesis in accordance with the kind of model. Now, it might be that they evolved in some way, and that the constants of nature changed from eon to eon, and that maybe there was the first one. The trouble there is you get back to the same problem as where did the first one come from, and things like that. Whereas in this scheme, there wasn't the first one. It has in common, you see, when I first got interested in cosmology, and I went to Cambridge to study, well, actually pure mathematics at the time, but I got involved with people who were cosmologists. Dennis Sharma, particularly I was friends with, and Herman Bondi and Tommy Gold and Fred Hoyle, and they had this model called the steady state model, which had the expansion going on all the time like this, and one of the great virtues of this model was that there was no beginning. And they considered that this was a great virtue, which I rather liked the idea. And then the thing was basically disproved because, well, various things were difficult with it, but the main thing was the microwave background. And so the microwave background seemed to say, no, the steady state model doesn't work. So I accepted that, Dennis accepted it, and so we had the Big Bang. But this is, in a sense, philosophically, very similar to the old steady state model. It was there all the time. No matter how far back you go, there were these eons, and they kept on going. Of course, it may not be right. The evidence which I just presented you today is only some indication that maybe there was an eon just before ours. It doesn't tell you whether there was one before that one, but it does at least resolve certain issues about where the first one came from, because it says, well, there wasn't the first one. Whether you regard that as a satisfactory answer is another question.
Okay, my question is just to reiterate. Basically, are you saying that these flashes which you observed in the microwave background radiation, did they originate, or do the numbers indicate that it resulted? They resulted before. That they originated before the Big Bang?
Now let me explain. And according to this model, you see, one of the reasons that people in general think inflation is a good idea, I only told you something which I worried about inflation. But the reason that it's around as part of standard cosmology is that it explains a very critical thing about the temperature variations. I mentioned that the temperature variation in the cosmic microwave background is about 1 part in 100,000, 10 to the 5. So you see these slight variations in temperature, and these points seem to be more than that, I should say. But it's roughly 1 part in 100,000. And they have a certain characteristic that was called scale invariant. So if you look at small or large regions, the variations seem to be the same. So this is a very important feature of the radiation, and this is the reason, the main reason, I think, that inflation has stuck with us as a central part to cosmology, because it's the only model that seems to explain that, or seemed to explain that. And the thing was that you seem to see this scale invariant expansion. As I mentioned right at the beginning, there seems to be this exponential expansion, and according to inflation theory, there were these things called inflatons, and the quantum fluctuations in these inflatons are supposed to produce the variations in the temperature in the sky. But what I'm saying is it's something very different. I don't have inflatons because I don't have inflation, but what I do have is this exponential expansion of the previous eon. But I need something in that in order to give these fluctuations. And the argument from this model, I haven't talked about it, is that dark matter, you see, when you look at the equations of crossover from one eon to the next, you find there has to be some new matter, which is some scalar material. It doesn't have directional qualities, but it only interacts gravitationally. It's a form of gravity in a certain sense. But this is this dark matter. I call these things eribons because I looked up in Wikipedia to see if there was a god which was the god of darkness. I first looked up and it said that there was no Greek god, but there was an Egyptian one called Erebos. And then I looked up later and then he turned into a Greek god. So I was happy about that because it had more respectability, I thought. Anyway, I call these things eribons. And these eribons decay. And they would decay, the lifetime has to be something like 10 to the 11 years. So we're looking at 10 times the sort of age of the universe in the ordinary scale thing. So, cosmological times, each one takes that long. But they decay regularly, so some of them will go off earlier than that. And these take part in this expansion, And when they cross over, that is to say the result of the decays of these particles that would be in gravitational signals, they would come out and produce these fluctuations in the temperature. But that's a technical point which needs to be looked at more carefully. I can't give numbers there. It just seems to me that on this model, the variations that are seen in these 10 to the minus 5 variations over the sky in this model are caused by area-bound decays in the eon prior to ours. And since you have this exponential expansion, which is scale invariant, given to us, you don't need a new field to produce it, as inflation does. It's given to us in this model, and so you see that it has this exponential expansion, and the area-bound decays should produce signals like this. Now, whether they do in detail is something which requires calculation and certain figures which I don't have. It is something for the future.
You mentioned that photon does not experience time.
Yes.
Stay still for it. Of course, it defines a time unit for the outer world, which is experienced at any point which passes by. And if I understood you properly, your point is that this time unit loses its meaning when there are no clocks to measure.
Yes.
And now I am wondering how I should understand this. If it is something like when a tree falls in a forest and nobody sees it, so that it did not happen, or it is more like that when there are no clocks, we have no reference frame, so that the period could be anything what we like. It is not good fun.
Well, let me go back. You see, I was saying that although the measure of time disappears when you have no mass, if the particles around have no mass, and there's some subtle points about addressing that in the scheme too, but that's the main issue. And it's not as though you still have temporal progression in the sense that you know which is past and future are still distinguished. So some people say, well, you have no time, how can you say these things follow each other or something? No, past and future, what comes before, what comes after, is still there. It's a question about how much time expires between it. And the thing is that certainly it's not if the tree falls in the forest and nobody's there, that it doesn't make any noise. No, I'm not saying that at all. The point is that the geometry, the physics doesn't notice how big it is. You see, if you have only physics without mass, then large and small become equivalent. And so the universe big and the universe small are physically identical. What makes a difference is if you have mass around and then you have the potential for clocks, but when the physics is devoid of any mass, which is the argument in the remote future, and there are some issues which I could address if people want me to, but once it becomes devoid of mass, then physically there's no difference between large things and small things. And this conformal behavior, which means no difference between large and small, is something which we seem to see in the laws of physics once mass is removed. And you see this particularly in the Maxwell equations, big and small are completely equivalent, and in the Yang-Mills equations, if you regard them as classical equations. Quantum mechanics presents some issues which need to be treated, but then big and small are still the same with regard to those forces as well. You have to worry about gravity, but then gravity is what makes the difference between the big and the small, and why the gravitational degrees of freedom get wiped out is all to do with the way gravitation behaves with regard to these conformal stretchings and squashings. But the idea is that it's a physical fact in this model that when there is no mass around, that physically the large and the small are equivalent. And so it's legitimate. I mean, it's a hard thing to get your mind around, and I agree. It's probably why the cosmologists don't like this model, because it's an unfamiliar idea. But it seems to me it physically makes sense to say that once there is no matter around, no matter in the sense of massive entities, then the big and small become equivalent, and the physics can smooth. You need equations to make sense of that, and that's another story too, but I don't have time to say all that here. I hope that addresses your point.
Hi. Oh. Does this scale invariance does it apply for black hole singularity? Can you just zoom it out like you do that for Big Bang?
I didn't quite catch what you said. Does it apply what?
The scale invariance for singularity in black hole. If you can just zoom it like you do that for Big Bang.
That's a very good point.
Thank you.
In fact, that was a very big part of the whole story from way, way back. I worried about this a lot. The fact, you know, when Stephen Hawking and I proved theorems about singularities, the sort of argument was, well, what happens in a black hole is more or less like what happens the other way around in the Big Bang, and that if you have singularities in one place, you'll have them in the other. Okay, that's all right for general arguments, but when you look in detail at what you expect to find in a generic collapse in a black hole, it is completely different from what happened in the Big Bang. So yes, I mean, your point is a good one, that the singularities in black holes, although there's no rigorous discussion of what actually happens, there certainly is the work done by the Russians, Belinsky, Lifshitz, and Kalatnikov, which seem to indicate that in general situations you get extremely complicated behavior. What's more important, that the Weyl curvature, which I didn't dare talk about, gets enormous. And so it's very, very different from what happens in the Big Bang. And this is all tied up with the second law of thermodynamics. We have a very, very conformally smooth Big Bang for whatever reason. And the reason I say is it's the continuation of a remote future of a previous eon. I'd like to see another explanation. Inflation doesn't do it, I should say. Inflation would only stretch it out like that if the universe is very special to begin with. It doesn't work in general situations. So there is something very, very different about the singularity in the Big Bang and what we expect to see in black holes. So if you stretch the black holes ones, they wouldn't do anything, they would just be a great mess. You can't continue the black hole singularities in a conformal way. The Weyl curvature, which is a measure of the curvature in the conformal sense, is enormous and probably gets wilder and wilder as you get closer and closer to the singularity. And there's no hope of continuing that in a smooth, conformal way. So yes, I said it's a good question, very crucial to the whole picture.
Okay, we have another.
Professor, I have heard that shortly before that of Stephen Hawking, he worked on the problem of certain photon cloud created near the black hole from all the matter falling into the black hole and creating thus something like we can say a memory of universe.
Yes. Yes,
can we expect or can we say that this object was called I think smart hair? Smart hair, yes.
Soft hair.
Soft hair, oh, yes, sorry, yes, soft hair. Can we say that this soft hair, which creates probably something like the memory of the old universe, can determine the quality of the new universe which is created?
Yes, well, I mean, I should emphasize that this is one of the points where I have strong disagreement with what seems to be a very prominent view amongst many physicists, which is what you just described, namely that somehow the information which looks as though it gets swallowed by the black hole, and if you draw conformal diagrams and things like that, I really don't see how it doesn't get destroyed. Somehow, the argument goes, it gets recreated outside the black hole. Now, it's an argument which many people have pursued, including, as you say, Stephen Hawking and collaborators, that they believe that there's something that I haven't looked into the details of what they call soft hair, but it doesn't seem to me at all plausible. There are other things called what do we call them? Firewalls. That was another argument people made. The trouble is, there is a huge conflict between two of the basic theories of 20th century physics. And this is a big conflict between Einstein's general relativity, which says we have black holes and they swallow, and you look at the singularity structure and you see what it looks like happening, and they swallow the information. So that seems to be what we see. And the other is quantum theory, and quantum theory is based on a very big principle, which is called unitarity. That's another way of saying the Schrödinger equation. And the argument is that if you have unitarity, you cannot lose information. And so you have this conflict. Do you stick to the fundamental principle of quantum mechanics, which says unitarity, or do you stick to what general relativity says, that somehow you lose the information in black holes? But it's not just that I was brought up with general relativity that I think that one's correct at that limit. It's just that there's a lot of problem with unitarity anyway, because in ordinary quantum mechanics, whenever you make a measurement in quantum mechanics, or almost whenever you make a measurement, you violate unitarity. Now this gets into a whole discussion of how you interpret quantum mechanics and so on and so forth. I am of the opinion that the current quantum mechanics is in need of replacement by some theory which takes into consideration the effects of gravity and at the same time violates unitarity. So once you're prepared to violate unitarity, and I don't see how you can avoid it unless you go into some scheme where all different, many worlds things, where you have all different things happening all at once and things like that. That's the only way you could get around it, as far as I can see. Once you still stick to your unitarity, then you've got to have either firewalls or whatever it's called, not damper, what was it again? Soft hair, that's right. Things like that, which are somehow kind to retrieve the information. So there's this strong feeling amongst many physicists that somehow you mustn't lose the information. You've got to get it back somehow. But it's very hard to see, because if you get it back outside, you violate another fundamental principle of quantum mechanics, which is called no cloning. You're not allowed to repeat information here and here. And so if the information is there approaching the singularity, how are you allowed to repeat it outside? It seems to me you've got a serious problem with that. So I'm afraid I disagree with these arguments, which seem to suggest that somehow the information comes back. Soft hair, firewalls, whatever it is. It seems to me that the general picture that one has from gravity is correct, and that information is simply gulped down by the singularity. I'm sorry about that, but that's what the theory seems to say.
Okay, one more quick question.
Thanks for the fascinating lecture. I think you just discussed this, but just to clarify, perhaps, entropy is variable, right? And you mentioned the rate of change or progress towards entropy. Could you perhaps explain?
Yeah, I can say what I said before, perhaps.
But is it oscillating or is it resetting?
Oh, no, there's no oscillating. Yeah, I mean, there were soon after Einstein's general theory of relativity, Friedman discovered solutions of the Einstein equations, and one of the particular ones was what's now often referred to as an oscillating model. So it expands out, and then it collapses down again, and then it bounces and does that. Okay, that was a very clear solution to the equations. But once you consider black holes and second law of thermodynamics, well, Tolman had a model where he never quite did that. It changed from each stage to this. But that was only a very, very tiny entropy increase effect. Once we know from the Bekenstein-Hawking formula how much entropy there is in a black hole, there's no way you can do it just by something like a bouncing model. I mean, because as it comes in, you've got a great congealing of black holes, and the entropy is going violently up because they mess with each other, and then you've got to wipe them all clean and start again. It doesn't make, to me, much sense to have a model which has this incredible mess at the end, and suddenly it bounces out into something smooth. I should say it doesn't make much sense to me, but there are people who do, in loop quantum gravity in particular, where they consider somehow that there was a bounce of some sort, which I don't quite see how what happened before the bounce could be a model anything like the universe we know now. It would have to be something very different. So it's very different from the scheme I'm saying. Certainly models which do that oscillating, I don't see how to make sense of them within this sort of general scheme of general relativity. because you get black holes forming and you get an unbelievable mass at one end and a nice smooth thing at the next end, and they just don't match. So that's the problem I have with it.
Okay, I'm afraid that's all the time we have for questions right now. So we'll now officially close the program. Thank you all for coming, and let's please give one more round of applause to Sir Roger.